Alright, in this video we want to add to our last video where we did coordinates, and we want to see if we can come up with a change of basis matrix. So if you remember from our last example, we ended up solving x times the vector 1, 1 plus y times the vector minus 1, 1 was equal to 0.5, 0.87. And from this vector equation, we saw that we can make a matrix equation that looked like 1, 1 minus 1, 1 times a vector with components x, y, the unknowns, was equal to 0.5 and 0.87. We were able to augment and solve, and then just as we had seen from our picture, we ended up with the vector xy, or the coordinates in terms of our new basis, was equal to 0.69 and 0.19. So the question that we're asking is, well, is it possible to figure out how to get this matrix so that we then could make the change of basis between any two given bases by using some sort of matrix multiplication like we've done here? And so the answer to the question, of course, is yes. So the way we're going to think about it is we know that a basis can actually form any vector in a vector space. So let's assume that our standard basis, change the color back here, I'll call it S just for our purposes, is equal to S1 and S2. So it's that ordered basis. And let's assume we want to rewrite whatever our vector is. So if we had a generic vector, x would be equal to some x times S1 plus y times S2. And this vector would then be denoted as x, y, and those are the coordinates in terms of our standard basis S. So let's start by first considering a second basis. We'll call it B, and that basis will be an ordered basis with B1 and B2. Of course, both of these are bases. In our example, we're doing just R2, but this can be generalized. And so we'd like to figure out how we write x, our vector above, in terms of the basis B. It's certainly going to have different coordinates than x and y because the basis is different. And so what if we took this approach? What if we first figured out how we could write S1 in terms of the basis B? So it might be something like A times B1 plus, say, let's put subscripts here, say A1 times B1 and A2 times B2. Let's say that's how we combine the basis vectors B1 and B2 to form our basis vector from the standard basis S1. And similarly, let's say that we had S2, and we were able to put that together by multiplying, say, by C1 times B1 plus a scalar C2 times B2. All right, so those were the two ways to put together those vectors. So clearly we could see that if x was equal to, don't remember what I had there, we had x's and y's, okay, so coordinate x times S1 plus the coordinate y times S2, if I were to make these substitutions, this one here for S2, and this one here for S1, try to squeeze this in, I would get something like x is now going to be equal to x times, well, S1 is the same thing as A1 B1 plus A2 B2, and then that would be plus y and I'm going to do a carriage return here because I'm running out of space. And that y would be multiplied by C1 B1 plus C2 B2. And so what we see here is that this is just S1 and this down here is S2. So we just simply replace, but certainly if we multiplied that all out and collected terms, we would see that now x would be written in terms of, let's change that back, the basis vectors b. So we would have a way, just by doing this, and we kind of did it by brute force, but we'd have a way to actually get this done. But now let's look at our expression up here at the top, and let me see if I can get this copied. Select all of that. Let's see, that's not going to work for me, so let's cancel that. Let's do this. I'll just rewrite it on the other side. So we've got, get my color right, S1 is equal to A1 B1 plus A2 B2, and S2, vectors here, is equal to C1 B1 plus C2 B2. Now look on the right hand side, because we might be able to get a vector equation out of this. If we look at, let's say, the left hand side first, since I'm here, that looks like a vector that there's S1 and S2, and then over here on the right hand side I have A1 B1 plus A2 B2 and C1 B1 plus C2 B2. So it looks like we have two different systems of equations. If we look at this first system, we have that some matrix that contains the vectors B1 and B2 as its columns times A1, A2, the unknowns, will be equal to S1. And similarly, there's a matrix having as its columns B1 and B2 times the unknowns C1, C2, that has as its solution, its right-hand side, S2. So here we have two equations, or two systems of equations, with two different right-hand sides. So from our theory from our chapter 2, when we learned about vector equations, we know that this is the same thing as considering the matrix B1, B2 times the unknown matrix that has in it A1, A2, and C1, C2, and that would have to be equal to a matrix of unknowns that has as its columns S1 and S2. And so this is simply saying, if you look at this, we multiply this through. If you take away the column of C1 and C2 right here, then you have an equation that says this matrix over here, coefficient matrix, B1, B2 as its columns, is equal to S1. And then when you add back the C1, C2, that's just how you solve for S2. So this just solves for both right-hand sides simultaneously, similar to what we did when we were actually trying to find inverses, for example. So if we look at that, it means that the system of equations we need to solve in order to find out how we transform each of the basis vectors in terms of the new basis looks like B1, B2, augmented with S1, S2. And so if we think about the transition matrix, or the matrix that takes me from S to B, it would be the solution to some system of equations that looks like B. I'm going to call big B the matrix that has as its columns the basis vectors for B, augmented with big S, which is a matrix that has as its columns the basis vectors for S. And so this is how you solve for the matrix that takes us from the standard basis we're calling S to a basis B. Now the interesting thing is that there's nothing special about that S being the standard basis. That would work for any two bases. So for example, well, why don't I stop here and I'll come back and do an example in the next video.